Right. We'll just do a recap of the system, how it works. We have the cylinders up top. They're going to grab onto a pipe that's going to be cut. Doesn't necessarily need to be a pipe. It could be a solid steel cylinder also, for that matter. But at least it's a cylindrical object that's going to be cut, that it's going to grab onto. And we have a poppet valve that's not going to have any leakage if we close it off, in order to be able to completely lock in the hydraulic fluid once we've gained the correct amount of pressure on our cylinders there. We also have a 4-3-way directional valve. So it's a 4-port. So we have P, A, B, and T ports. So those are 4 ports. And we also have 3 positions for the valve. So we have the position where we are retracting the cylinders, the position where nothing is happening, the pressure from the pump is just going back to tank, and the position where we are extending our cylinders and clamping onto the pipe. Then we have our hydraulic motor in the center here. It's connected with the leakage line to a compensator so that we get the correct amount of pressure in the leakage line. And that is again connected to the tank so that it returns the tank with the correct pressure. And whatever has passed through the hydraulic motor also goes directly back to tank. And before the hydraulic motor, we have a flow control valve that is variable so that we can set it to a certain amount of flow. And it's going to release the extra amount of flow that we get is going to release back to tank. Then we have a pressure-reducing cylinder up top here that is going to, when it gets too high of a pressure on the outlet side of the cylinder, the pilot pressure is going to push it over so that it sends the pressure from the pump back to tank. And it's going to be jumping back and forth there, basically, if we get too high pressure. So every now and then it's going to let some of the fluid pass. And then we have a 3-2-way directional control valve. We have 3 ports. We have a pressure port from the pump. We have an A port going to the rest of the system. And we have a T port going to the tank. And we have 2 positions, either recirculating the fluid between pump and tank, or that we are sending the fluid further up into the system and into the motor. Now the last part of our system is the feed cylinder, we could call it that. It's going to feed the saw blade forwards so that it's going to cut into our steel pipe. Of course, in order to move our saw blade forwards, we're also going to have to move our motor forwards because it's attached directly to the shaft of the hydraulic motor. So we're going to have to push all of it forwards. And that's what this cylinder does. It's connected with a flow control valve here also, which is variable. It also has a bypass for when we're retracting it so that it can get full flow going backwards so that we can actually pull and yank the saw blade free if necessary, if it's slightly jammed. And it has a 4-2-way valve, so 4 ports, the P, A, B, and T ports, and it has 2 positions. It's either going to be retracting the cylinder or it's going to be extending the cylinder. And this is because we want to keep on adding fluid to the piston rod side while we are moving it about, because we want to make sure that it doesn't get jerked about by all of the motion and the weight of the motor and the saw blade. So all of this is connected to the hydraulic system on our ROV. So we have 3 connection points here. So it just looks like we have 3 separate connection points, but all of those 3 are connected directly to the ROV so that we have full control of our system here. But we sort of need to separate it a little bit to know what is what here. We couldn't have everything go through one directional control valve to begin with. That would have been very difficult. Yes? Why we have so many tanks? This is just a shortcut with showing all of these tank symbols, so that we don't have to make all of these lines going back to one tank symbol. Then we just show it going, exiting wherever it's going out from, and then directly into a tank symbol. But in reality, there will be a hydraulic hose or a pipe going all the way back to the same tank. So all of those are connected to the very same tank. So there is only one. So we had started looking at our at the motor that we were going to use. So it was page 20 here. Oh yeah, I'm just going to find this one. Let's see, I'll zoom it out one more there. Yeah.
Is it the same motor that controls the movement of the clamp arms that controls the middle system?
If it's the same pump or valve you're thinking about, the motor is only the only thing the motor is doing is spinning the saw blade. So the motor is not doing anything but that.
Well, you said something about the motor when you were talking about that.
About this one? Yeah, because the motor is, in order to spin the saw blade, the motor has to be connected to the saw blade. And it needs to be connected mechanically. So the saw blade is basically screwed onto the shaft of the motor, the shaft that's sticking out of the motor. Which means that if you're going to push the saw blade forwards in order to start sawing, you're also going to have to push the motor forwards. So both of them have to move at the same time. Because everything else here is going to be stationary. So nothing else can move. It's only the motor and the saw blade that's going to move as we push it forwards. And that also, of course, means that these lines over here, connecting the valves to our motor and connecting the motor to the tank, they're going to have to be hoses because they are going to be moving. Since the entire motor is moving, then everything needs to be able to move. We can't have pipes in that regard. We can have pipes going between the valves. That's not a problem, but all of these lines, the leakage line, the return line, and the pressure line going into the motor, they have to be hoses. And they have to be long enough so that they can extend the full amount that they need to. While most of the rest of the system can be pipes if we want to. Yeah, we were looking at the motor here. Usually when you're looking at a circular saw, especially if you just start looking at different kinds of shops, what kinds of circular saws they have. They usually have circular saws that are aimed at cutting wood, not cutting steel per se, but many of them can be used for that purpose also. You just need to switch to a different saw blade. And most of them are somewhere between 1 kilowatt and 2 kilowatts in power. Which means that we're going to have to want to stay somewhere within that. So if we have chosen this particular motor, the OMP25, it says up there, so that's that particular motor. If we want that one, we want to stay somewhere between the 1 kilowatt line that goes across here. I'm going to have to look here because that's a bit easier for me. So along the 1 kilowatt line and between that and the 2 kilowatt line. So if we want to stay within our efficiency of 73%, so we want maximum efficiency from our motor in this case, then we're going to have to stay within this part that's going around here and in this area below 2 kilowatts there. It's probably going to be easier if I use the... Shut off. Let's see. So we have the 1 kilowatt line going up here, and we have the 2 kilowatt line going there, and we have our 73% efficiency ellipse, more or less, going up there. And if we stay in this area, So within the 73% and below our 2 kilowatt line, then we're going to get somewhere between 1 kilowatt and 2 kilowatts, and we're also going to get the full efficiency that we can get from this particular motor. So for an example, if we try to hit this spot here, fairly in the middle of where we need to be, that translates to a pressure of just 60 bars. And our RV was delivering 220 bars. So it means that we really need that pressure reducing valve that we put in there, unless the ROV is reducing its own pressure before it sends it out. And then we can also look at the flow rate that we're going to need, because the flow rate up here, that's going to be 20 liters per minute. And with the valve pack that we were looking at on the ROV, we could get up to 80 liters per minute. So that means we also need to be able to regulate the flow rate in this case. And that's going to give us, from this point, if we go straight downwards, that's a little bit to the side of that line there, so a little bit more than 700 RPMs. So that's a bit on the low side maybe, but it's still better than the alternatives. If we crank up the size of the motor here, we are basically going to get less and less speed for it. The smaller the motor we have, the more speed we are going to get from it. And that's just my experience working with these Danfoss motors. So for this one, we're going to just stay in this area here somewhere. So as long as we are feeding it approximately 60 bars and approximately 20 liters per minute, we're going to get a very high efficiency, and we're going to stay somewhere between 1.5 to 2 kilowatts approximately. So that's going to give us a very good effect from our motor. So that means that we can use that one there. Of course, if we had known what size of blade we were using, the diameter of the blade and everything like that, we could on the saw blade, just to put in something here. Radius of 400 millimeters, that means that we're going to multiply it with 0.4 meters. We're not going to multiply it, we're going to divide it, of course. We're going to divide it with 0.4. I'm going to delete other stuff now. And that's going to give us the amount of Newton. So in this case, we would be getting 50 newtons. getting 50 newtons for each of the teeth on our saw blade. They would be getting 50 newtons in order to cut into our material. So as long as that is enough in order to cut into it, that's going to be completely fine for us. Now we're getting into the cutting physics and stuff like that. So that's way out of the hydraulics size. But it's just to show that just because we have found a motor that fits our system, it doesn't necessarily mean that we can use that motor. We might have to change for a stronger motor. So it's one of the problems when we are doing design of systems like this is that you might come to a point where you basically more or less decided everything, and then suddenly someone comes up with an idea that, have we checked how much force we are getting from this motor when we are cutting? And then you actually check it, and that's a bit on the low side. We're actually going to have to increase the size of our motor. And then when you increase the size of your motor, everything else follows, because then you have to start looking at, are the valves still correct? Is everything? And then you have to basically go over all of your system again just to check that you've gotten the correct parts in place. So for the motor-wise, we can choose the OMP 25 just because we know that we're not going to build this one, so it doesn't really matter that much which motor we choose. We can use that one in this case, which means that we can move on to our cylinders and look at those. So let's see, that was the correct one. So for an example with these cylinders, it would be nice to know the weight that they need to keep up. So that would be much like the calculations that a couple of the teams have been doing on the mechanical construction project, when you're doing a team project there, where you're actually using friction in order to hold whatever it is that you're holding. And that means that we're going to have to calculate where the cylinder is being pushed. That was a bit where the cylinder is being pushed into the steel pipe. So along this area here, we're going to have friction. So depending on how large that claw is that's putting in, and whether or not it has rubber or if it's steel against steel or whatever it is, if it's serrated steel, so that they basically cut lots of grooves in it in order to make it get a better grip, that's also a possibility. Depending on what kind of grip you have there and what weight all of the equipment is, that's going to tell you how much force you're going to need here. So we're just going to assume 10 tons, that we need a force equal to 10 tons when we're moving in here. So that means ten tons, 10,000 kilograms. And just to make it easy for ourselves, we'll just calculate it with a G equals to 10 meters per second, it's supposed to be, squared. So we'll just do a roughly equals to G for that one. And that is fully allowed to round off G to 10 meters per second square. Not a problem at all. The only thing you're not allowed to do is to round it downwards. So you can't say 9.5 or anything like that, because that's going to give you less force than you actually need. This is going to give us a little bit more than we need. So if 10 tons is what we need, then this is going to give us slightly more than 10 tons. And that's just all well and good in our case. Of course, if this pipe is very fragile, so it's a very thin-walled pipe or something, then we have to think about how much force we're adding to it. So 10 tons might be enough to start collapsing the walls of the pipe. So then we might have to do something else in order to connect it. But with 10 tons, this should be fairly fine. So that means that we have 100 kilonewtons of force that we need to apply with our cylinders. And in order to figure out where to do that, we need to go into our mechanical trades handbook for an example. And that is in the page 402. So this page here with you can actually see the cylinders if you have good eyesight in the back there. Where it says at the top part here, it says piston forces. And that's exactly what we're after. We're after figuring out how much force can we get from this piston. And it also says that in order to calculate our effective piston force, we need to put in, so I'll just write up effective. It's not all that good with handwriting always. I think I'm going to have to find a better software to do this in. So effective piston force. I've started off here now, so I might as well just finish it. With the effective piston force, we have the F equals the PE, which is the operating pressure that we're working at, multiplied with A, and multiplied with the efficiency of our piston, eta. And the efficiency of our piston, we can't know that unless we've actually chosen our piston. So what I would recommend to you is, if you're doing calculations like this on the exam, if that's a part of one of the exam tasks that you have to calculate piston force or something like that, put in that you assume that you are using the same efficiency as it says in the example here, if the task doesn't say anything about efficiency. Either that or that you assume 100% efficiency. So just put in that there is a reason why you have chosen what you have chosen. So if I've written in the task that the piston efficiency is 93%, then you just use 93%, of course. But if I haven't written anything in there, then make an assumption and actually write it in there. So we have this one. We are running, we're looking at the clamps now, so we're running full 220 bar pressure on this one. So we'll look at our F is going to be equals to 220 bars of pressure. And it's going to be multiplied with whatever area we figure out. And the area is, of course, the area of a circle, because it's the area of the surface of the piston. So we're going to get pi divided by 4 multiplied with the diameter squared, multiplied with the efficiency. And our F is going to be equals to our 100 kilonewtons. So we know that already, that we're going to have 100 kilonewtons, we're going to have 220 bars, and in this case we'll use the 0.85% that it says in the example in the Metal Trades Handbook. So the only thing we don't know now is the diameter. Yeah? We're going to use pascals for it. So we're going to convert it now afterwards when we're doing it. For this particular one, we need to use pascals because Pascal is the same as Newton per square meter, and we are putting in our piston force in newtons. So we need to convert the bar over to Newton. But if you look down to the last bit of the page here, they've actually, where they are calculating the power of pumps, they've actually put in conversion factors so that you are able to put in directly bars and rotational speeds and all of that. So the flow in liters per minute. So you don't need to recalculate it into cubic meters per minute or anything like that. So unless it says so directly in the text in the book here, that you can use a specific set with units for that formula, then you're going to have to always convert it to the SI units that we usually use. So for this one, I'm just going to move everything upwards a bit. That one also. Get a little bit more room here. So for this one, we need to yeah? For the force, we're just assuming that we need 10 tons of force. So we don't know that we need 10 tons, because in order to know that, we would have had to know the entire weight of the equipment that we're using. We would have needed to know the frictional factor that we get between the claw and the steel pipe and all of that. So it's pretty impossible to do that sort of straight off. So we're just going to assume that 10 tons is going to be enough force in order to keep our grip on that steel pipe. So what we're going to do is we need to solve this one for the diameter. So we need to put in the diameter. And since the diameter was squared, we of course need a square root over on this side. And all of this, the 220 bars, and the efficiency, and the pi divided by 4, all of it has to be moved over to the other side with the force. So we get the force up top, and we also get the 4 from pi divided by 4. So we get those two up top, so 4 times F, and we get the 220 bars down here. And we get pi and eta. So now we know we can put in the 100 kilonewtons up top. We need to convert the bars to something, and we also have 0.85 to put in there. So for the conversion of bars, we have 220 bars. Let's see. Didn't want to do that one. So 220 bars. If we convert that directly to megapascals, it means that we have 22 megapascal, because 10 bars equals 1 megapascal. So 220 bars is 22 megapascal. And even though we want it back into, we would prefer to have it in a Newton per square meter. With regards to looking at the SI units, it's meters and Newton that you prefer. But in this case, we are looking for the diameter of the piston, and we will usually give the diameter in millimeters. And megapascal, if we just look at Pascal, that equals Newton per square meter. But if we look at Pascal, of course, not just P, but if we look at megapascal, we have Newton per square millimeter. And that's basically because the mega in front of Pascal, that's 10 to the 6th of Pascal. And a square millimeter is 10 to the 6th smaller than a square meter. So that you get, you can sort of cross those two out from each other so that you get it directly in there. So we know that we can use megapascal directly in this one. We're going to have Newton up top. We're going to have Newton per square millimeter below. And then we can get everything in directly. So our diameter equals the square root 4 times 100. And then we'll do 1,000 to get the kilos away there. And we'll divide it by 22. Megapascals. Multiplied with pi. And multiplied with 0.85. That's going to give us, let's see, square root. That gives us approximately 82.5 millimeters. Put in millimeters also. So 82.5 millimeters is the approximate piston size that we need. Most likely we would have to either go for 80, 85 or maybe 90 in this case, just to see what we're going to do. But considering that we've already done the rounding off of G and making sure that we get a little bit more force than necessary, it might actually be possible to go down to 80 millimeters in piston size. We would most likely have to do some more fine-tuned calculations just to make sure that we're going to be on the safe side there, but it might actually be possible to do that. So that means that we know the piston size for this one. The pistons themselves don't really need to be all that long, so most likely we don't need to consider ourselves with it being bent out of shape and breaking that way with the piston rod. So the piston rod is going to be very short, so that we don't need to look at that for this one. That might be a problem for the feed cylinder, however, if it's going to have to push the motor and the saw blade for a long way forwards, then it's going to be a problem, possibly, depending on how much force it's going to push with. Usually, one thing that you could think about if you're designing a saw that's going to saw something is that approximately 15 to 20 kilograms, that's usually the amount of force that you're using when you're pushing a saw through something, a circular sawway, or using your hands to slide it through. So the force for the small feed cylinder doesn't need to be all that much. We need a very low force on it. So we'll look at a little bit back here. Considering then that we have 220 bars coming straight in here because we're not regulating the pressure right now. It might be that we actually need to regulate the pressure, because with 220 bars, if you're only going to give, we could actually do the calculation for it. We could calculate how much our piston would, what size our piston would be if we're only going to deliver 20 kilograms of force with it. And you'd see with 22 bars, that's going to be quite little. So we're basically not going to get any piston in there, more or less. So I think I'll create a new sheet here. Yeah. The feed cylinder, or that's this one. That's the feed cylinder. So it pushes on both the motor and the saw blade, or basically it pushes the motor and the saw blade follows the motor. So that's you can't really push on the saw blade when it's rotating. That won't work. So you have to push on the motor itself in order to make it move. Yeah. Yeah, it will basically be the force that the cylinder is pushing on the motor with, so that's going to be the effective piston force of 20 kilograms in this case. So it's going to push with approximately 20 kilograms on the motor, and that's going to be enough to make the motor continually cut all the way through. So we're going to have a look at how much that's going to be. Just need to start up a new calculation here. I will just keep it up there. Let's see, widen out a bit. So if our intended power is going to be 20 kilograms, so only 20 kilograms, that means that we need to multiply it again. We'll use 10 instead of 9.81. So we'll multiply it with 10 meters per second squared, not cubed. Meter per second squared. And that gives us 200 newtons. So basically, we've removed the entire kilo part from our previous equation. So this means that we're going to have quite a lot smaller piston on this one. And to be quite frank, I'm pretty 99.9% sure that we're going to get such a small piston from this calculation that it's not going to be physically possible to construct a cylinder like that. So it means that we're going to have to reduce the amount of force that we're doing, but we'll come to that a bit later on. So we'll put up the same calculation as we had previously. We're going to solve it for the diameter. So we have the square root, we have the 4, we multiply it now with 200 newtons. And we have the 22 megapascals. We have pi. And we have the 0.85 efficiency. So what we get then is 4 times 200 divided by 22 by pi by 0.85. So we get an approximate cylinder diameter of 3.7 millimeters. So that basically means that our needle and our piston rod would be, that our piston and our piston rod would be a needle. so it's that thin. So that's not something that we could create, and the piston rod would break as soon as you started putting some pressure on it. The piston rod wouldn't be able to hold all of that, all of those 20 kilograms anyway. So that means that we're going to have to, 3.7 millimeters, of course, not meters. So that means that we're going to have to think a little bit differently on this one. So on the other two cylinders, yeah? That's the diameter we get if we calculate it for 220 bars. It's for the piston on the feed cylinder. The other one was for the two clamps, for the pistons there. Because the two clamps were running those at 220 bars, so we want full force on those. But for this one, we want a particular amount of force on it, and that force is so much less than what we want on the clamps. So it ends up becoming just a ridiculous cylinder that can't be created if we are going to use the full operational pressure. But if we also add in a pressure-reducing valve in our system, then we're going to be able to do it. So what we're going to do now is we're going to do basically the same calculation, but we're going to try to solve it for a different pressure instead. So we're going to try to figure out what kind of pressure do we need. So if we think that the previous ones were approximately 80, so between 80 and 90 millimeters in diameter. So if we do the same for this one, we make it just as big. So if we say 80 millimeters on this one, then we're going to try to figure out what the pressure is going to be. And then if we just go back here a little bit. Just copy that one. Didn't get all of it. Let's see. So we had the force, and that was the A. I have missed something on the A also. Let's see. So we had force, pressure, area, and efficiency. So that means that we've now been solving it for the area in order to figure out the area. Now we want to solve it for the pressure. So we're going to put in the pressure here. PE equals, then we get F up top, and we're going to divide it by the area, which will be pi divided by 4, multiplied with d square, multiplied with the efficiency. So if we now look at 200 newtons, we got pi divided by 4. And we have our 80 square millimeters. Not our 80 square, 80, yeah, it's going to be 80 squared and square millimeters. I just need to do this a bit more efficiently here. Let's see. I forgot the parenthesis before millimeters. So that's going to be squared, and then we have the 0.85. So we'll just calculate that one. So then we actually get a pressure of, let's see, I'll do it underneath here, approximately 0.05 megapascals, which means that 0.5 bar is the differential pressure we need. So we basically need a pressure that's not a pressure at all. We almost don't need any pressure. Yeah, you had a question? With the 80 millimeter here? Yeah, we are putting in the 80 millimeters from the previous calculation. So we got it to 82.5 approximately. We're just rounding it off to have a bit better numbers to work with when we're putting them in. So that means that we have a very small pressure here. So most likely, if we ran it with a 40 millimeter diameter instead, so then we will get approximately 2 bars of pressure. So it's not really all that much that we need, but the whole point here is that when you're cutting something, you can't really just jam it in there. You have to push it slowly and gently in order to get a nice cut. So it was sort of expected that we were going to have a very low pressure on this one. We're going to do a break, and then we'll finish off after the break. Right, so the last thing I mentioned before we went to the break was that if we switched from 80 millimeters in diameter to 40, then we had needed approximately 2 bars of pressure on this one. And that's achievable with a 2-bar pressure differential on a cylinder. That's something we can achieve with a pressure-reducing valve. So that's a possibility that we have there. So we'll just go back to the, let's see, to this one. So this means that we know that we need around 80 to 90 millimeters in diameter for these 2 cylinders in order to gain the correct amount of pressure, the pressure that we are just assuming that we need in there. We don't know the weight of anything or the coefficient of friction or anything like that, so we can't know for sure, but we've just set something in order to be able to calculate. And with this one, we've figured out that with a 40 millimeter diameter of the piston, we're going to need about 2 bars of pressure. So that means that we're going to have to do a little change to our schematic here, because we need to add in a pressure-reducing valve. So basically the same kind of valve that we have here, we're going to need that in here also. So in order to do that, I'm going to try to move everything upwards. See if that's going to work properly. Should be possible for me to add some more in there now. So then we get, let's see, I can remove a little bit there. If I instead let that line go. So the return line for the cylinder is going all the way back anyway. So I just directly connect that one. And then we put in a pressure-reducing valve here. And it's going to have return to tank. A bit cramped there, but that we'll just have to do. And it's pilot operated. Let's see. Sometimes it just doesn't want to do the line. Let's see. There we have it. And we're also going to connect it there, but without an arrow. Of course, that's something I forgot on both of these now, was that we also need a spring symbol here, of course. I'm not sure if I'm going to get the spring small enough, but because of course it needs to be pushed back into place when the pilot pressure is lowered enough. So for this one, we definitely need to have return to tank for it, because it's going to be lowering the pressure a whole lot. 218 bars of pressure is just going back to tank, so we don't need it from that one. So it really needs to have that return to tank, or else it's going to be pretty much impossible for that valve to be able to regulate the pressure. It might even be, if you were going to produce something like this, it might even be that you needed to have several of these kinds of valves in a sequence, because they usually can only go for a certain range. So for an example, you would have one that went from 220 bars and able to go down to 140 bars, was able to get the pressure down to that. Then you would need another one after that was able to take it from 140 to maybe 80. And then you would have a third one from 80 maybe down to 10. And then you would have a last one from 10 to 2. So that might be a possibility that you have to actually put several of these in sequence, because it is highly unlikely that one valve will be able to take it all the way from 220 and down to 2 bars. But fortunately, until you actually start looking at what valves are available, you can just assume that you're going to be able to do it with one. So you'll just have to add them in as you go along and figuring out, because that depends quite a lot on the suppliers of the valves, what kinds of valves they have and what ranges they are using on theirs. So might suddenly be that the supplier you're using actually manages to take it all the way from 220 down to 50, and then one from 50 to 2. So it might be possible to do it with just 2 valves. You never really know until you actually start looking at what the different suppliers are able to deliver. So now we've got, yeah? The 220 is the pressure from the ROV, yeah. So in this case, the ROV that we originally looked at, so this one, we of course had the proportional valves. So we had down here, I'll just zoom in a little bit also. See. So we had, as it says over there, we have proportional flow and pressure control for one of the valve packs. But the other two only have proportional flow control. So if we were going to connect that cylinder to valve pack number 1 or 2, we definitely would have to make sure that the pressure was reduced ourselves. So then we would have to put in those valves. And most likely it is valve pack 1 and 2. Those are the most likely where we would put in our cylinders, because they don't really need that much flow. They just need a little bit of flow until they've filled up the entire chamber, and then they're done. So it's the motor that needs a lot of flow, and that's why we would connect that one to pack number 3. But I think you had a question? With regards to which pressure were you talking? Yeah? We don't have a small pressure. We have 220 bars. Because if you go back to the data sheet here, it says 220 bars. And with these two up here, they can only regulate flow. They can't regulate pressure. So they're going to deliver 220 bars no matter what. Yeah, but all of the cylinders will be connected to those. So the third cylinder will also be connected to it. The feed cylinder will also be connected to one of those valve packs, which means that they're getting 220 bars. So that we have to put in some sort of pressure reducing valves in order to get the pressure down correctly. Yeah, for the previous calculations, I was in this one. I'll just move it over here. So with the considering having a 2-bar pressure there, then we're going to have to go with a lot of pressure reducing valves over here. Hopefully we'll manage with 1 or 2 or 3, but as I said, depending on your supplier, it might be that you need to have quite a lot of them in sequence in order to get down to the correct pressure. So they will basically just be, one will be reducing the pressure so that the other one can reduce it further, and then the third one can reduce it even further. So it depends a bit on what kind of equipment you find when you're doing it. But for a schematic like we're doing here, it's more than enough to just put in 1 and then specify that it's supposed to be taking the pressure from 220 to 2, because then if that's impossible, then of course they're going to have to use more valves in order to get it done properly. So for the initial design phase, like what we're in now, looking just at how the system is going to work, it's enough to just specify that we need the pressure to be down at 2 bars. So it's when you really start sort of picking components from your suppliers, that's when you need to look at, do I need to add something more in here? So usually in a design process like this, you have, I would think, at least 10, 20, maybe even 30 times where you go back and you redraw your schematic a little bit, because you figure out that you have to change something every now and then. So it can be quite a lot of work doing stuff like this, because every time you figure out something new, there might be another change. It might mean that something else also has to change. And when you've changed that other parts, that might lead into more changes for other parts again. So it's sort of a shockwave that moves across the system. So by saying here that we need a pressure reducing valve, we can suddenly end up with having 2, 3, or 4 pressure reducing valves there. We might suddenly start having with regards to our 3D model in Inventor, we might start having problems with space there. We don't have room for all of these valves. So we might have to start stealing space from the rest of the system. So we have to start moving around stuff and trying to get it to function properly. So it's sort of difficult to see before you're doing it, because you're constantly going back and changing stuff when you're designing something like this. But for the initial phase, which is as far as you're going to get on an exam anyway, this is more than enough when you're setting up a system. It's like getting the functions in there and getting the valves in there so that you know what you're going to do. And this would be a very complicated task for an exam, so it won't be that complicated on the exam. so don't be too scared now with this one, because here we have massive amounts of stuff to do, and we've also been looking at ROVs and a lot of other stuff. So we've been putting more into this one and what would be possible in the exam, because the exam is a 2-part exam. So we have both subsea technology and hydraulic systems in the same exam. So you're quite limited on time on hydraulic systems. You basically just have 2.5 hours of it, if you think 50-50 split for everything. So then you have, of a 5-hour exam, you have 2.5 hours for hydraulic system and 2.5 hours for subsea technology. So it's going to have to be, it can't be a complicated system like that you're working with on an exam anyway. It has to be more simple. I wouldn't think it would be as simple as the one we did last week, or if it is that simple, it would be at least 2 systems to look at. But I haven't made the exam yet, so I have no idea how it's going to look like quite now. Are there any questions with regards to the system design or anything like that? Then I think we'll leave it here for now, and on Friday I'll be doing a sort of recap of most of what we've been doing this semester. So that'll be it's impossible to do a proper recap in 2 hours, but I'll try my best to sort of look a little bit at everything while we're going through it. So just to give you and try to give you some hints also at what kinds of stuff I'm going to be thinking about with regards to the exam. So yeah, that was everything. Then the bus leaves at 1 o'clock from outside here. So Frederick was super happy with all of you guys when we were going to Kårstø, that all of you were on time and everything. So he was really, really happy. He was just pissed off at the bus since the bus was a little bit late. so hopefully the bus will be on time today, and we will all be ready, and we'll go off.